Okay, so when we left off last time, we were discussing how different factors can affect the period of a mass on a spring. And one of the things we thought might affect it was mass. We saw that the more mass was on the spring, I believe it was the bigger the period was. Yes, the more mass was on the spring, the bigger the period was. And now, we are checking out the spring constant. Okay, it was kind of right at the end of last video, but it was kind of tough to see. So what I'd like you to do is take a look. This spring constant, the spring just looks harder to stretch. This is the one with the bigger spring constant. It's a smaller spring constant. We'll see which one has the larger period. So I'm going to click Start. And as you can see, the bigger spring constant has a smaller period. It takes less time for this spring to return to equilibrium. Okay? So bigger spring constant, smaller period. So again, I'm not going to quite say that they're inversely related, but as one goes up, the other one goes down. Okay? We're going to hold off on saying whether it's exactly inverse or not. I'm going to show you one more. I'm going to reset this. We're going to pause, do slow motion. Now we're going to have the same spring constant, the same masses. Let's see, let's do this. This time we're going to do something a little bit different. This time we are going to displace them a little bit from their natural length, and we're going to see which one has a bigger period, because we said that this might occur. So I've displaced these differently from their natural lengths. Okay? And actually, you know what I'll do? I'll turn on this equilibrium position thing. I'm going to say let's displace these from their, we don't want the natural length on there. We're going to displace these differently from their equilibrium positions. Okay? Which one has moved more? Let's see what we get. So here we go. So we're looking essentially to see which one of these returns to the bottom first. Interesting. Okay? So, this is kind of a neat result. The amount of displacement, initial displacement, does not matter. Okay? So you might say, well, how could that be? If you displace it more, there's going to be a bigger force here. Well, that's true. There is going to be a bigger force there, but it's got more ground to cover. Okay? It's a bigger force, but there is a lot more space to cover. This is a smaller force pulling up on it, but it doesn't have to go quite as far. So it actually turns out that the initial displacement has no bearing on the period of the pendulum. Very interesting. You probably wouldn't have guessed that. Okay? So let's go back to the notes. So we talked about what factors could affect the actual period of the pendulum. Here is the actual equation. Okay? And this is listed on the reference tables. The equation for the period of a mass oscillating on a spring is as follows. T equals 2 pi times the square root of the mass over the spring constant, m over k. That's why I didn't want to say that they were directly proportional or inversely related, because there's a square root in here. Okay? I'm not going to speak about why the 2 pi shows up. There are ways to derive this from Newton's laws and equations, but it's pretty far above the level of this course. So we're just going to leave it. Okay? The important thing is, for a spring, the period only depends on the mass and the spring constant. Very interesting. Okay. So, that's masses oscillating on springs. There's one other type of simple harmonic motion that we need to talk about, and that is for pendulums. And pendulums are kind of an interesting case, because not every single pendulum oscillates in simple harmonic motion. You'll notice that on the back of your notes, there is a spot, and it says for pendulums, and it says small angles only. Okay? Small angles, what does that mean? We're talking about angles under about 30 degrees. For anything above about 30, this is not simple harmonic oscillation. And this idea that you can only use angles under 30, and by angle we mean the angle of initial displacement. So when you have a pendulum swinging like this, okay, a pendulum swinging like this is simple harmonic motion, okay? This is a very small angle, initial angle that I pulled the pendulum bob to. This is probably about 30 degrees right here. This is about the limit of simple harmonic motion, okay? Right about here. I'm trying to get the shadow on the board for you there. If you do this, turns out this is not simple harmonic motion. Again, for reasons that we don't really need to get into, okay? We don't need to talk about why this isn't simple harmonic motion. You just need to know that it is not, okay? And this idea that you can only use small angles, this is called the small angle approximation. I guess I'll get into a very brief discussion of why only small angles work, okay? It turns out that for this one, the displacement is not directly, no, what is it? The restoring force is not directly proportional to the displacement, the angle of displacement. The force is proportional instead to the sine of the angle, but when you have very small angles, the angle itself and the sine of that angle are very, very similar. So we can kind of fudge the numbers in a little bit as long as you stay below 30 degrees, okay? As long as the initial displacement of the pendulum is not more than 30 degrees from the vertical, okay? We're measuring from the vertical line. As long as you're not going way up here, as long as you're sticking to about 30 degrees or lower, that is simple harmonic motion, or at least we can approximate it as simple harmonic motion. It's close enough for our purposes, okay? Not something you really need to worry about too much. So, for a pendulum, here's our picture. Okay, there's the ceiling. We have a string tied to an object. We'll call this position A. And as time goes on, that object will swing down to different spots. You know what, since I got it for Christmas, I really should be using, probably should be using this, right? I mean, oh, look at that nice straight line. Thank you once again for one of my Christmas gifts. Matter of fact, look at that. There we go. Look, I only wasted a couple seconds putting this on. Okay, so we've got 5 different positions for this pendulum. Starts at A, swings down to B, C, D, and E. That's only half of one oscillation. If it were to swing all the way back to A, that would be one full oscillation. Okay? And we're going to do the same thing that we did last time. We are going to talk about each point and talk about the variables, the measurables that we can evaluate at each point. So we're going to have A. Now here are some things that we can measure. There's going to be 7 of them. Okay? Thankfully there's no springs here, so we don't have to talk about elastic potential energy. But we do have to talk about the initial x position, or not the initial, but the x and y positions, the velocity, the acceleration, the kinetic energy, the gravitational potential energy, and the restoring force. We're going to assume that, let's see here. Let's assume that the position C is where the origin is. This is 0, 0, right down here at C. Okay? Well, if this is at 0, 0, A, where you release the pendulum from, and again, I know this is very clearly way more than 30 degrees. Okay? I'm exaggerating this because otherwise it would be really hard for me to write all these little ones in. Okay? So please remember, this is for small angles only. I'm exaggerating it here. Alright? So at A, let's see, if this is 0, the x position of A, well, it's negative, and this is about as far to the left as this object's going to go. So this is negative maximum. What the heck? Fell right off my shoulders. Okay, so that is a negative maximum. What about y? The y position, the height. This is as high up as it's going to go. Okay? So we could just say that maybe it's positive. It's a positive maximum. Speed. This is where we release it from. Speed is 0. Okay? The acceleration. It is about to start accelerating in the, I guess we would say the positive direction. It's going this way. Okay? So let's say that the acceleration is positive. And you know what? It is at a maximum. The object is about to start moving this direction. If you remember what force causes the simple harmonic motion, or drives the oscillation here, it is a component of the force of gravity. The component is very big at point A, right here. So we have a very big force, okay? Therefore we have a very big acceleration. The kinetic energy is 0. Gravitational potential energy is at a maximum. And we'll say that the restoring force is also positive and at a maximum. It's in the positive direction. I guess we're really saying the positive x direction because I know that down is negative. So we're really talking about when we say the force is in a positive direction, we're saying that the force, we're kind of considering the fact that it's getting driven this way as it's positive. Okay? So, x position, negative maximum, y position, positive maximum, no velocity, acceleration, positive maximum, no kinetic energy, maximum gravitational potential energy, maximum restoring force, positive and maximum. Let's go to point B. Same sort of thing. At point B, well, B is kind of in between, right? So it would be really tough to say that the x position is at exactly what it is. So instead with these for B, and again we'll see this for D, I'm just going to put arrows. I'm going to tell you whether something is increasing or decreasing. So the x position at B, okay? What's happening to the x position? Well, it's moving to the right. The x position is increasing. And the y position, as you probably have guessed, is decreasing. The speed was 0. You can only go up from 0. So the speed is increasing. The acceleration might be tougher to see, but think about it like this. We're going from maximum displacement, okay, maximum amount of force, down to an equilibrium point. What do you think is happening to the acceleration? Yeah, it's probably going down. Okay, the acceleration is decreasing at this point. The kinetic energy is increasing. Since the object is speeding up, it's gaining velocity. The gravitational potential energy is decreasing, and as we just said, the force, the restoring force, is going down as well. Okay? So, x is increasing, y is decreasing, v is increasing, a is decreasing, kinetic energy is increasing, gravitational potential energy is decreasing, the force, the restoring force, is decreasing. So, let's move on to point C. Point C, this is equilibrium. I didn't write this in earlier. Let's fill that in. Equilibrium. Okay. Oh, and something else I had written down. We're assuming no damping, so ET equals ET. At point C, well, this is kind of easy. X and Y. Well, we said this is the origin. So therefore, X has to be 0, Y has to be 0. Okay? That's just how we defined our coordinate system. What has happened to the speed? This is the lowest point. So the speed is at a maximum. All that potential energy got turned into kinetic energy. If it's at equilibrium, what is the acceleration? There is no acceleration. Okay? It's got to be 0. The kinetic energy, if the velocity is at a maximum or speed is at a maximum, kinetic energy's got to be at a maximum. The gravitational potential energy must be 0, since we're at y equals 0, no height. And finally, if the acceleration is 0, that means that the restoring force is also 0. Lots of zeros and maxes there. We've got 2 more points, but aren't they just mirror images, or like the flipped version of B and A? D is just like B, E is just like A. So these should be really easy. We should be able to do these very quickly. Okay? Matter of fact, let me fill them all in right now, and then we'll blitz right through them. Okay, so at D, okay, instead of, well, I guess the x position is still increasing. But instead of the object moving down, now it's moving back up. So the y position is also increasing. This is the fastest point. It's going up to where the speed is 0, so the speed must be decreasing. The acceleration might be a little tricky to handle. Let's just think in terms of like how much acceleration there is. There is no acceleration right here. At this point, at A, or at D, excuse me, now there is acceleration. Now it's starting to slow down. Okay? So the acceleration is in the negative direction, but let's just put an up arrow for the acceleration is increasing. I know it's going to be more negative, but let's just think of how this is working. It's going to have greater acceleration in magnitude right now. So I guess we're just talking about magnitude. If the velocity is going down, the kinetic energy is going down, the gravitational potential energy must be going up because the object is moving up. And if the acceleration, if the magnitude of the acceleration is increasing, the restoring force must be increasing as well. If you take a look, most of these are exactly the opposite of all the quantities for D are almost exactly the opposite of B. The only one that's still increasing is X because it's still moving in that direction. Finally, we get to E. Again, remember this is not one full oscillation, it is only half of an oscillation. As it moved from E back to A, you would have to flip a lot of these, okay? Or essentially every, these two really would flip, okay? So, this is the farthest that it goes in the X direction. X is at a positive maximum. The Y is also at a positive maximum. You might say, but wait a second. It was already at a positive maximum at A. Yeah, it goes back to the same point. Okay? Not that big a deal. There can be two maximums for something. This is the highest that it goes. This is the farthest that it goes. It's the turning point. Therefore, the velocity is 0. Therefore, the kinetic energy is 0. I know I skipped acceleration. I'll go back to that in a second. The gravitational potential energy. If this is the highest it goes, it must also be at a maximum. Finally, acceleration and restoring force. Okay? The restoring force, okay, the component of the force of gravity, perpendicular to the tension in the string, is pulling the pendulum bob back down this way. It's going to be very strong here, and it's going to pull in the negative x direction. So for the force, I'm going to write down negative max, same thing for the acceleration, negative and a maximum. This is where the object starts to, has a maximum acceleration, a maximum restoring force that pulls it back towards equilibrium. On the way back down,